Hi, and welcome to our talk about optimizing load times and streaming performance using direct storage, a new storage API for modern storage devices by Microsoft. Just a moment while this loads. Here we go. So what do we want to talk about today about this particular storage API? Well, we want people to understand why we need this new API. We want people to understand how it enables fast load times and better performance during streaming. We want to talk about the data flow improvements it provides. We'll talk about our demo and have a quick discussion of the things we learned about it. We'll provide some profiling suggestions for when you're implementing the API yourself, and if there's any time at the end, we'll provide time for questions. So why do we need a new storage API? Well, storage bandwidth has been rapidly increasing, and the latency of the devices in returning the results for those requests has been decreasing rapidly. Modern storage APIs and their linear and serialized fashion are not necessarily appropriate for these new fast storage devices. We would also like to be able to provide the benefits of new versions of Windows more seamlessly across the versions of Windows and also across the console. So an API that works across all of these would be more optimal. And in essence, also a more direct route of placing the assets in memory as their resources should be a little bit faster. So associating the two and getting them into memory together should help speed up the process. So to talk a little bit about why we want a new API for this and to convince people that it's a good idea, let's have a little talk about things like VRAM capacity and the throughput of these devices over time. So in this chart, we have VRAM capacity of various GPUs throughout the years, with the y-axis representing VRAM capacity in gigabytes per second. And we can see that some modern GPUs support up to 20 gigabytes per second, or sorry, 20 gigabytes, and some of them even beyond that at this point in time. And in terms of maximum GPU bus bandwidth, we can see that there's a kind of linear increase in that over time. However, currently the most usual limiting factor as far as the interfaces between all these devices happens to be the PCIe bus from the storage device to the system memory. So on the left-hand side, we can see the bandwidth is in gigabytes per second. And with modern PCIe 5x4 NVMe devices, we can see that there's approximately 12 gigabytes per second available. However, the most recent ones that have shipped are in the 9 to 10 gigabytes per second range. This is what we'll be using for the remainder of this talk. Here's a chart of the storage bandwidth and VRAM capacity on a linear scale. And it's important to note that they've been kind of increasing at a very similar rate. However, it's probably more important to see that the ratio between these two is what actually enables better performance, and that's easier to see on a log scale. So in orange, we have the storage bandwidth in gigabytes per second, and in blue, we have the VRAM capacity, and as the ratio of those two decreases, of course, the load time decreases as well, and that's where we want to be. So in 2019, we were near sub 1 second load times. In 2022, we're looking at about near 2 second load times. This particular chart here is basically the best possible load times we could possibly achieve when we don't have any kind of compression enabled, given the VRAM capacity and the throughput of the PCIe bus and of those devices, of course, as well. So in 2022, like I had mentioned, it may be possible to get 2 second load times. And in 2019, we were near 1 second load times. However, currently, most titles aren't able to use or aren't even taking advantage of the capabilities of the devices that are in these systems that are capable of that kind of throughput. So if we kind of artificially limit our throughput to about 500 megabits per second, we'll be stuck with 30 plus second load times for quite a while. And if VRAM keeps increasing, it's going to only get worse. So how do we get there? How do we go from these potential 30 second load times down to 2 seconds? Well, We want to implement batching. We want to encourage decoupling the metadata from the resource data itself. We want to encourage coupling resources to the storage requests. We want to see how the data flow can be improved. We're going to implement in compression. And then, while we won't be speaking about it much in this talk, the API does offer a means of prioritizing those requests. So why do we want to batch? Well, this generally batching will lower the CPU overhead because we'll have fewer context switches and fewer system calls for many requests. We want to keep the device extremely busy. So if we batch up the requests and create lots and lots of them at a time and then submit them all at once, we're going to actually have a much more efficient usage of our resources. And then, of course, they can be those submitted requests can be sorted and with respect to priority, and they can be serviced very quickly. The following charts have been created using the following configuration. It's important to note here that the maximum measured bandwidth is around 4.5 gigabytes per second for these. So this is a chart of performance when queue depth is approximately 1, inferring that there's no batching. And when we talk about queue depth, we're talking about the number of requests in flight at a time, and this is the simulation of serialized requests. So as you can see on the left axis, on the y-axis, we have megabytes per second. This is the bandwidth in megabytes per second, and on the x-axis, the size of blocks, so the size of each request. And we can see that at 256 kilobytes, that the maximum throughput is approximately 568 megabytes per second. This is not exactly fast for this particular storage device. As you can recall, it was able to service requests at around 4.5 gigabytes per second. So as you can see here, as you know, more to scale to the maximum throughput of the device, we're not utilizing this device very well. And as you can see, as we go to the left of the chart, our throughput greatly decreases and our ability to utilize the device to its maximum through potential is decreased. However, when we have the queue depth set to 64, then our potential to utilize the throughput of the device is greatly increased. And we're able to achieve that at about 128 gigabytes per request, or 256 gigabytes per request when the queue depth is approximately 64. This chart is a bandwidth heat map. And so in this heat map, each of the colors represents approximately 20% range of the performance. So 1 through 923 megabytes per second is the lower 20%, and the 3,689 through 4611 megabytes per second is the upper 20% of the performance range. So along the left side, we have the block size in bytes, and along the top, we have the queue depth, and that, of course, is the number of requests in flight at a time. So if we want to utilize the device potentially very poorly and only achieve up to 923 megabytes per second, then we would limit ourselves to a queue depth of 1. And that applies to all the block sizes listed here. However, if we want to get it into the sweet spot and utilize the device fairly well, then we're going to have a queue depth of approximately 32 and a block size greater than or equal to 64 kilobytes per second. So let's talk a little bit about batching and decoupling our data dependencies. And the reason, of course, we will do this is because we want to improve I/O performance regardless of our API choice. However, Direct Storage encourages the use of batching through its implementation and your usage of that API. So before we can batch, though, we've got to decouple our data dependencies. And what kind of dependencies am I talking about? Well, I'm talking about read-to-read dependencies, because these create stalls. A very simplified version of a read-to-read dependency would be reading the texture header for a texture, and then reading the texture data, and then finally reading each bitmap, because the texture header contained, for example, the size of each bitmap. This tends to also be caused by things like editor pipelines and workflows. So we'll see later how we address these types of issues. Game engines are more complex though than a texture header. A lot of times we have things like level metadata, followed by asset metadata, which is going to get loaded, followed by texture metadata, followed by the headers for those textures, and then finally the texture data itself. And you can see that's really how engines have tended to work, and that's very complex, right? But we really want to reduce these complexities as much as possible, or at least store as much of the data ahead of time in a collapsed format in a table in memory, such that we can access the normal texture data or the base color texture data or any texture data as quickly as we can, without having to read all the headers in or the metadata for those headers in at once. And that way, when we load a level, we can also load the metadata for the assets at the same time in parallel, and then finally make all the requests for all the data we need in giant batches. So let's take, for example, the GLTF file format. The GLTF file format is an API-neutral 3D asset transmission format in JSON. It has a hierarchy, and in that hierarchy, we have our meshes, materials, and textures. And those textures are composed of various images. The images are stored in PNG or JPG format using uniform resource identifiers, which are very similar to URLs. And a modern GLTF loading pipeline looks like the following. We'll load our GLTF file, we'll read in the PNG headers, and we'll finally read in the PNG data. We'll decode the PNG data, generate the MIPS, create resources, and then finally upload the MIPS. However, it would be great if we could just load in the GLTF file and simultaneously load in all the metadata and generate the load requests for the data we need. However, before we can do that, we have to set the data up into a format that is pre-processed in a way that direct storage can read. So in order to pre-process the data, we want to first load the PNGs and create the MIP chains offline and store them. A lot of engines refer to this as baking or cooking. We will fill in the metadata structure to load when the JSON file loads at startup. So this is an example of a data structure that we created for our sample, and it contains all the data necessary to load a resource for when a particular URI for like a PNG or a JPEG is referred to. And this enables us to get rid of many steps in the loading process. But before we can make a request to load the data, we actually have to create the resources or allocate the resources for the data to be stored in on the GPU. And here we're using the create place resources function. The create place resources function takes, for example, a resource desk and the starting state and the heap offset for where we're going to store the data once it has been uploaded. However, we also include the compression format, the resource offset on the disk, the resource size, which is compressed and uncompressed, as well as the resource URI, so that we can have that along for the ride when we go to make the request to direct storage, as you can see here. So this is a dstorage request, and it contains essentially all the other fields from our metadata header. And we stored these in memory so that we can very quickly fill out the request and provide it and queue it to direct storage to load. So a little bit more about the data created during the pre-processing step. That data is in the format of get copyable footprints. This is a device-independent format, and we can always compress it after the fact in order to reduce its size using one of the available options in direct storage. So in what other ways does direct storage improve data flow? Well, let's first go over what traditional Win32 data flow looks like. First, we read the application reads a file or requests to read a file. The data goes into an OS IO buffer. The driver or IO manager copy that into the application IO buffer, and then the application copies it into an upload heap and that is followed by a GPU copy into the GPU resource, and this is up to 4 copies. If we add in CPU decompression to this common pipeline, which is common as well, it adds in another set of copies. So first, the application requests to read a file. That is read into an OS/IO buffer. The application IO, the driver or IO manager copy that into the application IO buffer. The application decompresses that into a decompression buffer, which is then copied into an upload heap, and a GPU copy is created into the GPU resource, and that is up to 5 copies. It's important to note that these are mostly done in system memory, and that may not be the most efficient place to do it. Direct storage improves the data flow. First, the request is enqueued, and the data is copied into the API's IO buffer, which is then copied into an upload heap, and a GPU copy is made into a GPU staging input buffer. The GPU staging input buffer stores that has the compressed data and is decompressed into a GPU staging output buffer. It is then copied from there into a GPU resource, as you would expect to use. What's important to note here is that a lot of the processing steps, such as decompression, are done on the GPU, which is where the data is going to be used. This enables a slightly more efficient usage of the memory of the bus itself and of the device resources. So what other types of data improvements have been made? Direct storage automatically uses the copy queue. So if your title isn't already using the copy queue, once you've implemented direct storage, the copy queue will be automatically used. It also takes advantage of Windows 11's new I/O capabilities that improve throughput and CPU utilization, and it does so transparently. That means that you do not have to implement it yourself for users of Windows 11 and Windows 10. You just have to implement direct storage, and you'll get optimal usage of both. For Windows 11, bypass IO significantly bypasses several portions of the kernel IO stack. And Windows 11 also offers the IO ring file IO API. And because you use direct storage, you won't have to worry about implementing either one, because it's done for you. But the IO ring API batches requests and completion notifications to reduce the CPU overhead of context switches, which would be created by addressing each request individually. So on the left-hand side, we're showing the bypass IO model, and on the right-hand side, we're showing the traditional IO model. And as you can see, the bypass IO model kind of circumvents the volume stack. However, with bypass IO, certain conditions certainly apply. And those conditions include the fact that it only works with NVMe devices, and it can be disabled under the other following conditions. BitLocker encrypted volumes will not bypass the volume stack. NTFS encrypted files, NTFS compressed files, sparse files during volume snapshots, and if any filter driver is installed in the IO stack, which vetoes bypass IO or does not implement support for bypass IO. Because some of these conditions are dynamic, bypass IO can be disabled dynamically at any time. However, it is done so transparently, file reads will not suddenly start failing. Microsoft has provided a utility, FSUtil, with the bypass IO state options to allow you to test whether or not a file path supports bypass IO. And it might be important for you during testing to test whether or not it is enabled, because it will impact your profiling and testing performance. Direct storage also provides for cancellation, and this might be an unsung hero for low-end platforms and fast-moving titles with texture streaming. It saves quite a bit of bandwidth and it improves responsiveness. It's important for titles where lots of data may become irrelevant very quickly. If the camera moves from one position to another very quickly, then the textures related to the old position will become out of date, even if the requests are still in flight. And in some engines, and commonly in most engines at this point, the data is allowed to be loaded and then ignored. But if we but if we're able to cancel the requests while they're in flight, we can conserve a lot of bandwidth and improve the responsiveness of the devices and of the loading of those resources. So let's talk a little bit about compression and decompression. So let's talk about the obvious reasons though. Less data to transfer across all the interfaces, and that includes the network transfer time, as well as the PCIe bus. It also saves disk space on end user systems. And sometimes it provides a little bit of data obfuscation, and it's important to note, of course, that that is not encryption, and it's not a guarantee that data hasn't been tampered with. So why do we want to move data decompression onto the GPU? Why don't we want it on the CPU? Well, we are only as fast as our slowest component, first of all, but also during load time, most of the time we're not using very many GPU cycles anyway. Most of the CPU cycles are needed for things like compiling shaders, decompressing game data, and initializing game objects. And as we can see in the little diagram above, if we limit ourselves to the slowest performance of any path or device along the way, it makes sense to delay the decompression all the way towards the end. And there are decompression rates that we are observing often on higher end GPUs of around 16 to 24 gigabytes per second. So what are the compression options offered by direct storage? Well, we could choose not to use any compression, and that might be advisable for things like compressed video or JPEG data, which has already been compressed to begin with. We could use the built-in compression, which is currently GDFlate. And this is a general purpose compression algorithm targeting GPUs. The tools for it are built into the API, and it can be downloaded from GitHub for free to integrate into your own tools if necessary. And then there's custom decompression, which enables you to create your own or use your own type of decompression for the CPU. It is advisable to use this potentially for CPU bound resources. However, please do not try to use this to implement your own GPU decompression. It won't perform nearly as well as the built-in one. So again, about non-GPU targeted resources, anything that is just targeted for the CPU, if it uses GDFlate decompression, will do the GDFlate decompression on the CPU, and that may not be optimal performance. I would definitely advise to compress the data using the custom compression technique for better performance that is more suitable to that data. Some techniques, for example, would include LZ4, LCO, ZSCD, etc. Just pick one that meets your needs. And for reference, it's possible to achieve over 6 gigabytes per second per core on modern CPUs using LZ4 with low compression settings. So how does it impact performance? Well, it really depends. A lot of factors include the storage device bandwidth, right? We're only as fast as the slowest thing on our path. The size of the staging buffer, and that helps limit or actually expand the amount of pipe lighting we can do. And then the GPU performance itself. How fast can we decode the data and upload it? And we'll be discussing this a little bit later in our discussion of our direct storage demo. So in general though, why use direct storage? Well, it saves us from having to maintain all of these different things to get optimal performance from all the different storage APIs across different Windows versions, and may allow us to share code on some of our other devices. It also provides the usage of, it also manages the upload heaps and copy queues related to resource upload functions. It encourages good file I/O optimization practices through things like batching, and it reduces CPU load. So our direct storage sample is a simulation of streaming high detail assets while the camera moves through a scene. The camera moves through the scene and trigger volumes. As it enters different trigger volumes, it will load or unload assets. It is developed using GPU Open Cauldron framework as a test bed, and we use it to understand the integration requirements for direct storage and the performance it can provide, along with providing ISVs with a sample on how to implement it. By moving the camera at different rates, we can control the demand on the streaming system and on the hardware. The faster the load time, the sooner an asset appears. The following system configuration was used for the following charts and videos. Actual results may vary. So here's a quick video of our demo. First, it's important to note that our demo is composed of multiple assets. And the first set of the JSON file here describes which assets, and the bottom part describes the streaming volumes, their radius, and the position in the scene. Then we're going to open the standard GLTF file that is used for these assets, and we'll open it into Microsoft 3D Viewer to give you an idea of what these assets are. And you can see that it takes a little bit of time to open these assets in the 3D Viewer because the assets are quite large. Then we'll do a pre-processing step, as we had mentioned in a prior slide. We use a thing called Texture Converter, which we created, which reads the configuration file, and we supply a compression format and the compression level to it. In this case, we chose GDeflate with default compression level. However, when more compression formats become available, they will be available in this little Texture Converter program. And as you can see, we can load the sample. On the right, you can see a little legend that says that green means loading, yellow means loading, green means loaded, and gray means that the asset is not loaded. And when we enter the streaming volume, which was initially gray, it goes into the loading state and then followed by the loaded state. It's important to note that our sample also has the ability to have an autopilot with a speed control, as well as a simulated workload, which includes Mandelbrot iterations to help you see and explore what it looks like and the impact it has when GPU decompression is used with various levels of workloads. And the reason we did this is because the rendering workload provided by the sample itself may not be very high. And you can see here that we disabled the autopilot and enabled a free camera so that you can enter and exit the volumes on your own to feel the responsiveness. Our sample features, as mentioned before, a way to pre-process GLTF textures into a direct storage compatible format with the metadata, and that was seen in the header that we showed in earlier slides. It can do this. It can pre-process the data with compression or without compression. It has an adjustable staging buffer size that we can adjust via command line parameters. It has an adjustable artificial workload to study and understand how decompression interacts with other rendering and compute workloads. And it has PIX profiling markers on the CPU and the GPU to aid in understanding how these things interact when we're doing timing captures in PIX. It also has adjustable camera movement speed that can be set on the command line parameters to help with automation and testing. We can also enable and disable the direct storage or change the location of the decompression, whether that's on CPU or GPU via the command line parameters. And we can enable or disable placed or committed resource allocation on the command line. We may also enable or disable workload cancellation to test the ability to conserve bandwidth, especially on lower end systems. So here's a quick video comparison. This video comparison on the top left has direct storage using CPU decompression. On the top right is direct storage using GPU decompression. And on the bottom, we are not using any kind of direct storage implementation. We are just using the GLTF file along with the PNGs or the JPEGs that are provided along with it. And you can see the difference in responsiveness. This also enables you to compare a little bit visually the GPU frame time graph that we've provided in each of the windows. This will enable you to see the impact of GDeflate on the rendering performance. As you can see in the prior sample videos, there are various measures that are taken and statistics that can be either viewed on screen or in a CSV file. These include the load time of the asset, which is from the request of the load until the asset is presentable on screen, the I/O time, which is from the first direct storage request until direct storage has completed processing that request all the way through the pipeline on the GPU, whether compression is enabled or not, the disk I/O only data rate, which is the throughput of the disk during direct storage requests, and then the amplified data rate, which takes into account whether or not the data was compressed or not, and how fast that data was decompressed on the GPU. We also include the frame rate before, the average frame rate before and during asset streaming, so we can understand the impact of using direct storage on the frame rate. And of course, the number of frames it takes to load each asset, so we can get an answer of how much latency there might be. So here's a quick sample of our CSV output. It's important to note that in our CSV files, we called it map size or map name for each of the assets, and really that is asset name. So let's talk a little bit about these asset sizes, because as before, I mentioned that some of these assets were kind of big. This chart shows the compressed asset size, the compressed texture size, uncompressed texture size, and then other. It's important to note that we only implemented direct storage for the textures because they represented the largest amount of resource data to load. So the other stuff is, of course, index buffers and vertex buffers. The compressed textures, when the textures are compressed using direct storage, we can see that the command module is just under 1 GB of data. The uncompressed size, though, would have been about 2.7 GB of data. A similar scenario plays out for the Space Shuttle. That's quite a bit of data to be loading in the amount of time that we're doing so. So what kind of compression ratios are we receiving when we use the default compression level for GDFlate? Well, on the command module, it was about 3x, and the Space Shuttle, about 2.8. And for X1, it's about 6, and for Boombox, it's a bit more. But it's important to note that these textures were not in BC formats, or block compressed formats, and so your compression ratio may be lower if you use BC formats. However, the advantage from using data compression or GDFlate compression is not necessarily defeated. It may not be as great. So how long did it take to load these resources when we were using direct storage or not using direct storage? And these charts, lower is better, and the y-axis is time in milliseconds. We can see that direct storage, which is represented by the teal color, using GPU decompression, was able to load these 2.7 GB textures in just under 400 milliseconds when using GPU decompression. And when we use the CPU, it was just under 800 milliseconds. And when we didn't use direct storage at all, and we used the original PNG and JPEG assets, it was over a second. So we can see there's quite a benefit to using direct storage along with GPU decompression. However, it doesn't necessarily come for free. In this chart, the y-axis represents the percent performance loss during the time that decompression was occurring. The command module was showing approximately 15% performance loss while decompression was occurring, and the Space Shuttle almost 20%. However, decompression times were quite short. And we can see from this chart, where higher is worse, and the y-axis is time in milliseconds, that the command module decompressed all of its textures in just over 160 milliseconds, and the Space Shuttle very similar. Here are some tips and recommendations. These came from our implementation of direct storage in our sample. For streaming textures, using place resources often offers a faster resource creation time. However, it only does so if the heap is created well ahead of time. Our demo doesn't do this, and you can see it in our PIX captures, or if you take a PIX capture of it and yourself. Staging buffer size should be approximately or greater than or equal to 256 megabytes for best performance. It might be better to use custom compression techniques on the CPU-only resources because GDFloat does not execute as fast on the CPU as it does on the GPU. It's important to fill in the debug request field for each direct storage request because that makes it understand the real source and reason for I/O requests. Modern engines have all kinds of indirection when it comes to multi-threading, and not understanding where a request comes from could go a long, or understanding where a request comes from could go a long way. For titles with extremely low, targeting extremely low end hardware where the min spec or the required spec does not require a dedicated GPU, for example, in many laptops or APUs, it might be important to consider adding a checkbox to your menu options and preferences for end users to force disable direct storage using GPU decompression, i.e. allow those users who want to force it onto CPU decompression, as that might be more performant. Direct storage supports unaligned reads, but for maximal performance, it's best to consider using aligned reads. So profiling. We use PIX timing captures, and we would recommend that you do too. And so we're going to provide some options and ways to configure it in which it will be productive. We like to disable the GPU memory usage capture option. And the reason we do this is because it seems to create more context switches, which is more overhead that you'd be profiling and may not help you dig into the data that you're actually after. We also recommend enabling GPU timing so you can see the effect of decompression on your rendering workloads and potentially other GPU workloads. It's important sometimes to see why things are stalling, and so we also recommend enabling call stacks so you can see all those different context switches and where they come from. And we also recommend that if you're going to be profiling the launch time performance, that you select the launch suspended option. So here are a few timing capture options we recommend. We also recommend disabling CPU samples to reduce the amount of overhead created when they're enabled. You can enable them later if you need them, but to start off with, we recommend disabling them. We also recommend enabling file IO to see all the recorded file accesses. And this could actually be one way at the current time to see if bypass IO is working, because it doesn't show up. The file IO doesn't necessarily show up in the PIX timing capture when you have it enabled, and bypass IO is enabled as well. However, when bypass IO isn't enabled, or you're on something like Windows 10, then the file IO accesses do show up in the PIX timing capture. GPU timings. As we mentioned before, it's important to see all the direct storage controlled queues and workloads and the impact of decompression on rendering. We would recommend that you change your capture output directory to a device that is not the one that you're going to be primarily reading from. And to use remote capture, again, to reduce the amount of overhead on the target profile device. This slide shows a bird's eye view comparison where we have direct storage with GPU decompression enabled on top, and then no direct storage usage on the bottom. And when we say no direct storage usage here, we mean loading the JSON file for the GLTF file, and then decoding the PNGs or JPEGs that are included within. As we can see, with direct storage enabled and GPU decompression on, the amount of time spent in file IO, which is highlighted in the blue region, is significantly less than if we don't have direct storage enabled at all. We can also see that the depth of the IO requests is significantly greater, and this somewhat represents the number of outstanding requests at a given time. Whereas with no direct storage enabled, the read requests are scattered everywhere. They're rather small, and it takes quite a bit of time. So how does direct storage look when it's doing GPU decompression? Well, first, a copy to the GPU memory is done. Then, The GPU decompresses data to an output staging buffer. Then it is copied from the output staging buffer from decompression and into the destination resource where it can be used for rendering. In this particular slide, the GPU decompression is shown as a dispatch, but more commonly what you will see these days is that instead of a dispatch, there will be a meta command. Direct storage creates its own queues. So what we have found is that successful direct storage integrations will reduce read-to-read dependencies, they will batch up their requests, and they will ensure the transfer sizes are appropriate. Using timing captures will also ensure that you can find some places of significant CPU work that might be stalling other storage requests. Direct storage is distributed and can be found with the link here to the direct storage landing site. And these are the system requirements for direct storage. Currently it requires Windows 10 or Windows 11. Shader Model 6 or compatible or Shader Model 6 and capable GPU to support GPU decompression is required. And it does not necessarily require an NVMe device. Spinning devices will still work transparently. I would like to make a special thanks to all the people that helped make this presentation possible. If you have any questions, this is a good time. Thank you.